Well, now we're going to pivot back into the academic world to learn about some interesting research being done by PhD candidates. We're going to hear about some innovative approaches to browser fingerprinting, which Peter Lowe just spoke about, a new solution to filter list circumvention. But first, we're going to hear from Hieu Lee, who is a PhD student in computer engineering at the University of California, Irvine. Like Peter, Hieu also spoke at last year's summit. So Hieu, thank you so much for being here again and for sharing your research.
Thank you so much for the introduction, and welcome to my talk towards automatic generating and testing of filter rules. This is joint work with my advisor, Athena Markopoulou, and our collaborators, Zubair Shafiq and Sama Almalaki. So in order to understand how to design a system that can automatically generate and test rules, we first look at the common workflow of a filter list author. So for example, given a filter list author and a site and a browser, they are tasked with creating rules that can block ads and not break the page. And here we define breaking the page as just legitimate visual components of the page that are missing, such as images. And here I'll focus mainly on network blocking filter rules. So of course, the filter list author does not know what to block beforehand for this site. So what it can do is look at all the outgoing network requests from, for example, the Chrome developer tools, and they'll select one request, perhaps using some kind of keyword like, oh, the URL has the word ads in it. And they'll block that URL, and then they'll have to visually inspect to see whether that was effective or not. So what do I mean by that? So for example, given a site here, they'll look at the site without blocking anything, and then to identify ad locations and where certain images and text are. And then they'll block the URL, and then they'll look at how did the page change. So here you can see that there's still one ad being served, and then there's a few images that are missing that should not be blocked. So they'll have to do this iteratively until they identify all requests to block. And next, they'll have to generate basically potential filter rules. Now, of course, there's many different ways that you can write network blocking filter rules. For example, by effective second-level domains like example.com, or more specific like ads.example.com here. And then once again, they'll have to select a filter rule one at a time. They'll apply it on the site, and then they'll visually inspect it again. And they'll do this process over and over until they are able to finalize a list of filter rules that are good for that site. So we can use this human workflow to identify challenges in creating an automatic system. For example, what to block. Here we can see that the filter list author has to identify potential filter rules, select one by one to try it out. And of course, this is a major bottleneck because it's manual work. Second, we have to figure out how to determine the effectiveness of filter rules. Here, the filter list author has to manually do it by visual inspection. So this is also a major bottleneck as well. So we can now establish some requirements to in designing an automatic system. First, we know that we have to automate these major bottlenecks. Second, we know that the automatic system has to do some kind of learning through experience, because the filter list author or the automatic system doesn't know beforehand. So they have to generate the filter rule, learn one by applying it on the site, and then getting some kind of feedback from it. And that has to be all like automatic as well. And then third, hopefully the system is better than brute force, because there may just be too many potential rules to explore. So the good news about this is that all these requirements fits naturally into reinforcement learning. So I will explain how we can model this human workflow as a reinforcement learning problem. So first, I'll define some terminologies that are standard to RL. And we know that we need to kind of automate what the filterless author is doing, for example, like selecting from the rule and applying it. So in RL, this is what we called a policy. So we replace the agent with the policy, and it makes the decisions which filters should be selected, and it learns from the feedback, basically. And so our potential filter rules now become just a set of actions. The policy from those set of actions selects one to test, and that is just a filter rule now. Next, so how do we derive these actions? We just take cues from what the filterless author is doing by looking at all the possible outgoing network requests and generating the rules based on different granularities. Like I said, example.com or ads.example.com, or including paths and create parameters and so on. And in doing so, we're able to automate the human creating the rules with actions. And then now we need something that is responsible for applying the action. And so in RL, this is called the agent. It has the goal of finding the best filter rules for the site to block ads. And to do so, it follows the policy and applies a selected action on the site. And in RL, this is called the environment, which consists here of the site and the browser. And it's important to note here that the environment has dynamics that are unknown to the agent, and are not controlled by the agent either. For example, what kind of content is shown or ads served by the site are unknown to the agent. So next, we know that we need to replace the visual inspection part of this. And in the human workflow, it's the responsibility of the filterless author to do so. But in RL, the environment has to give this feedback, and it's called the reward. So the reward basically measures how effective a filter rule is. So how do we go about figuring this out? We once again look at a site, and we apply a filter rule. And then we'll represent the site now based on just the number of ads that are still being served and the number of legitimate images that are served to the user. And we can do this automatically, perhaps by using image classifiers like Percival, where they can take an image and say, is this an ad or not an ad? And so now the reward is a function based on the number of ads and the number of images. And to close the loop, the policy takes that reward and learns from it before selecting the next action. So we have now replaced the manual work of visual inspection with a reward. And then let's revisit the goals of an agent. I've already mentioned that it needs to learn over the best action over time by interacting with the environment, but it also needs to maximize the cumulative rewards over time. So basically what this means is that it enforces the policy to select actions smartly and not just randomly. And currently we're still exploring many of the policies that are available to reinforcement learning. And in doing so, we are replacing basically the human selecting the rules part with following the policy. So next, we'll show some preliminary results by implementing this workflow and applying it on different sites. And I'll simplify the results by displaying how filter rules are effective on a site based on two factors here. The y-axis denotes how much of ads are being blocked, and it's normalized between 0 and 1. So this means that 1 meaning the filter rule is able to block all ads. Now the x-axis means that there's legitimate content like images that are missing, normalized between 0 and 1 as well. 1 meaning there's high breakage and there's a lot of images that are missing. So the top left corner here, any filter rule that falls in that block means that's the optimal solution. It blocks all ads with no breakage. The top right means that it was able to block all ads, but it had high breakage. And the bottom right means that it only caused high breakage and it didn't help with blocking ads at all. And the origin here just means it has no effect when considering these two factors. So we applied on crickbuzz.com, which is a simple sports site that has like a few ads. And we find that when we try the first-party filter rule, it was able to block all ads, but it caused more than 40% of the images to go missing. Next, we find some filter rule that has no effect on the site, like google.com, gstatic.com. And then we find some optimal rules here, where googlesyndication.com and doubleclick.net is able to block all sites with no breakage. Next, we applied on msn.com, which is a more complex site in terms of more outgoing network requests. And we find that when we have the filter rule for akames.net, it's able to block all ads, but cause very high breakage. And at the origin, here's interesting. The first party rule, msn.com here, had no effect on like the images. This just means that the legitimate images are being served by a different domain. And then doubleclick.net here, which was effective for quickbuzz.com, is not effective here for MSN. And then we find that scorecardresearch.com has no effect, and that's not surprising because it's a tracking domain. And then finally, we find that media.net is the one to block that has the optimum results here. So next, I'll identify some challenges when we apply an RL system in the wild. The main one basically is that when we have to visit a site, right? We're learning through experience, and you may have to do that hundreds of times. So this is very costly in terms of time and money as well. And usually in reinforcement learning, a way to deal with this is to reduce the possible actions that we need to explore. So for example, we may apply filter rules that we learn from site A to site B. However, as we saw before with my example, doubleclick.net worked well for QuickBuzz, but it didn't work for msn.com. So we're still not sure. So this is where we would love feedback from the community and especially the filter list authors. And so in conclusion, we showed that we can model the problem of filter generation as a reinforcement learning problem. And in doing so, we're able to automate major bottlenecks. And special thanks to Arthur Kawa, who helped give us insight on the workflow of filter list authors. Thank you.
Yeah, well, thanks to you, Hieu. We do have time, I think, for one question that we've had come in, and it concerns just the general nature of your research going forward. What are the next steps that you see in your research efforts with this framework?
Definitely, I'm hoping that we can apply this in the wild for thousands and thousands of sites, and hopefully come up with a solution where it is scalable, where it won't be hours and hours for one site only. Other future directions would be, how do we merge all the rules that we have learned per site? So my presentation so far has shown that we're creating domain-specific rules for now, but we need to figure out how to merge them into a real filter list and add them, for example, to easy lists.
Yeah, that makes a lot of sense. And I know that a lot of our internal people here at eyeo will definitely be keeping an eye on your research going forward. Thanks again for joining us, Hieu. We appreciate you being here.
Thank you.